Okay, let's go back to rocket. We don't have a rocket now, but so we know that to calculate any problem with varying mass, F equals to m dv over dt plus dm over dt multiplied by v. Okay. This term corresponding to the UUMA term, and this comes from the mass changing effect. Okay, so both of them will. So the force equals to the two terms add together. Now let's look at for the rocket. Usually we think about rocket like this. You have a rocket here with total mass with the mass m, okay, and it will release some working materials. We see it, so it's some gas, okay, it's released, and let's say the mass is small m, okay. So, and we call this object 1, this object 2. So there is some action and reaction between the rocket main body and the release material, right? So there is some force here, F12. There is some force acted on the releasing mass, F21. And in fact, it's this reaction to make the rocket move. Okay. So we can write down this Newton's second law for both the rocket and the exhausted material. Okay, exhausted product. For this one, it will be okay. And also we should say for the velocity here, let's use small v for this one. And for this, we use capital V. Okay. So it's just some convention. I don't know why. People use capital M and small v for rocket, small v at capital, or small m at capital V for the exhausted product. So with that, we get F12, the force acted on the rocket, should be the rocket mass multiplied by the derivative of the rocket velocity plus derivative of rocket mass multiplied by rocket velocity. Okay. And F21, that's the equation for the exhausted mass. So it will be small m dv or du. Okay, it's used u there. Fine, let's use u here. So du over dt plus dm dt multiplied by u. Okay. Any question here? I'm just writing down the two Newton's second law, the extended Newton's second law. Okay. And what we are going to do is to calculate the first rocket equation and the so-called second rocket equation. So the first rocket equation, you can say it will give you the acceleration of the rocket. And then the second rocket equation will give you the velocity change. Okay. So that's V final minus V initial. So that's the velocity change. And here we want to introduce some term. One term is the rocket mass loss rate. Okay, the R, which is dm dt. So for the exhausted product, it measures how fast you send this exhausted product. Okay, so it is a fundamental quantity to determine the velocity of the rocket. Okay, so how fast you can expel those gas. So R equals to dm over dt. That's an important parameter in the rocket design. And another important parameter is the relative velocity between relative velocity for the rocket measured from the exhausted product. Okay. So this velocity, both of them are velocity relative to the ground, or sometimes we can say it's absolute velocity. Okay, that's the velocity you are looking at. But another important thing is that the relative velocity between the two. So of course, that one, the relative velocity, the velocity should be v, the velocity of the rocket relative to the ground. Subtract this u, because u is to this direction, v is to this direction, right? Okay, so that's the relative velocity of the rocket with respect to exhausted product. Okay, any question about the two parameters? That's two important parameters. And then let's first substitute these parameters into this equation to rewrite it. Okay. Before substitution, let's do some rearrangement. The first thing is we want to combine the two equations. How can you combine the two equations? The two equations actually can be combined to get a very simple form. Think about F12 and F21. They are action and reaction. So what do we know about action and reaction?
Opposite direction?
Opposite direction with
same force?
Same
magnitude.
Same magnitude. Okay. So that means this one should be equals to negative of this one. Okay. So F12 equals to negative F21. And so if we substitute it, we should get m dv dt plus this equals to negative this minus. Okay? So there is some relationship between. And then let's rearrange it. Okay, here. So let's first move them to the left hand side. M dv over dt plus dm dt v plus m du dt plus dm dt u. Okay, equals to 0. Okay. Now, another thing we can try to identify is that there is some relationship between this d capital M dt and dm dt. Okay. Can you see? Think about what's the relationship between them.
Well, as the smaller end gets larger, the larger end gets smaller, right?
Yes, and so please note that, in fact, even more than that, the amount of the change should be the same. The rate, change rate is the 2, right? Because how much mass you increased for small m, you should have the same amount of mass decreased from the capital M, right? Because that's it's just a relation process. So if there's no mass lost to somewhere else, so it should be so. So both of them should be written as R. Okay. So let's see, dm over dt, this is the capital dt. So this one should be r, and this one is c, because that's decreasing, so negative r, right? Okay, so you should get negative r here. That's the mass increasing rate for the exhausted product. It equals to the mass decreasing rate for the main body. Okay? So you can rewrite this. And another thing, you can try to see. Let's first do this. Okay. So you get m dv over dt. This m du over dt, and then if we rewrite the two terms with negative r and r, so you have negative r multiplied by v plus r multiplied by u equals to 0. Right? Question?
Why is that negative r?
Think about the changing rate. It should have a positive negative, because increase if the it's positive changing, if the mass is increases, it should be called positive, and mass decreasing should be called negative. And here, because that's really, so this part increase positive, this part decrease negative. Okay, so basically it says that there's balance between the, this is the balance between the mass changing. Okay, any question here? And so you get negative, and those two can be combined. You see that if you factor out r, so you get v minus u. Okay, here we just write it down first. Okay, and by the definition, what is v minus u? This is the relative velocity between the rocket and the exhausted mass, right? Okay, so this term actually becomes this. Okay? So that's where it gives you the left-hand side of the first rocket equation. We still need to get the right-hand side of the Z rocket equation. Okay.
Where does that V net come from?
V relative?
Yeah. Where does that V net come from on the last one? Where's the velocity?
It's not net.
Because after I factor it out, that's V minus U, and by definition, it's a relative velocity, right? Okay?
Okay. Gotcha.
Okay, another thing is that we're writing this equation in terms of the, if we write this equation in terms of the velocity, so that means we consider some motion relative to the exhausted mass, right? In this reference frame, what is capital U?
0.
0. Okay, so we're talking about, in this case, so we're talking about the velocity of the exhausted product relative to the exhausted product itself, right? So in this frame, U should equals to 0, always, right? So this term actually goes away. You see that. So I'm talking about everything relative to the exhausted product, not relative to the ground. Is it clear?
It's relative to itself?
Yeah, relative to itself.
Okay.
So it's just like if you have a train, and if you can try to calculate then you have a people walking on the train. When you try to calculate the problem from the ground, so you need to think about there is some velocity for the train, there is some velocity for the people. But if you calculate the problem relative to the train, okay, if you calculate the problem on the train, you would think that the train is not moving, but the people have some velocity relative to the train. So the velocity of the train, you actually think is 0. Okay, we didn't talk too much about the relative motion, but the idea is something like that. So in this frame, u is 0. Okay, so these equations were writing relative to small m, not ground. Okay, question? Any question here?
So essentially, the reason why it's 0 is because relatively it's not moving, right?
Relative to itself, the
Relative
product
to
is
itself,
not
it's
moving,
not
right?
moving.
Okay.
Okay.
Okay. So we get m dv over dt minus r v relative equals to 0. And this is capital M multiplied by a, r v relative equals to 0. And that equals to this equation, the first rocket equation, right? So basically that tells you the dependence of the acceleration for the rocket on the relative velocity. Okay, so you can see larger the relative velocity, larger acceleration. So if you want to make a large acceleration for the rocket, you have to emit the product, exhausted product in a very fast speed.